Good morning, everyone. Those of you who joined us again, I did mention earlier, thanks to Matt and Celia sending me their presentation, which I will be using that as the first one for this morning's session. The sessions will be recorded, so they can be also used for future students if need be. However, if you could send me your presentations, albeit on your own or with a group of people that you've agreed, so we can watch them in the order that they come through. It is 9:15, in fact 16 minutes past 9. I will wait another 3 or 4 minutes to allow me time to upload the new presentation that you guys have sent me, and then we'll take it from there. So far I've only received one. So
Jared, you should have received mine, but Simon with us.
Simon, just bear me. Let me refresh my screen. I've got Matt and Celia's one definitely. What time did you send it to me, Simon?
About 5 minutes ago.
Right.
9:40.
Right, it's okay, don't worry. If you've sent it to the right email, jyazdani@uclan.ac.uk, yeah?
Yeah, that's right.
Check that.
Yeah, I copy-pasted it out of the chat. So.
Yeah, okay, if that's the case, it should come eventually. I refreshed the screen, nothing has come through, so... I'll come out and then do it again, maybe. Simon, I haven't, so you may want to send it again.
Okay, I'll try again.
Sorry about that. It could be something. It's on its way or whatever. So far, I've only got Celia and Matt. So, is that going to be the case? Just two people all together?
I'm just making some final changes to mine now, but I can send it then if that's all right.
That's fine. So we've got time. As I said, the email is open, so I will open them as I receive them. So there's no hurry if you're still making final touches to it.
Sure. Sorry, I was trying to do some other coursework for another module as well last night, so I didn't have much time.
I understand perfectly. Don't worry about it. Do you want to leave yours towards the end, nearer to 11?
Yeah, sure, if that's all right.
Yeah, it buys you time to prepare it. We've got plenty to go through, I hope, anyway.
Yeah.
Right. I'm going to start the displaying Matt and Celia's, and we'll take it from there, if that's okay with you guys. Right, I'm going to share my screen, and the session, once we are ready, will be recorded individually, so I can have series of little recorded versions. Guys, the session is going to be recorded, so can you refrain talking in between if you can. I will leave Matt and Celia to present it. Okay, so I'm going to put this on a presentation mode. Matt and Celia, over to you. Thank you. Introduce yourselves first and tell us which company you're from, so that also stays as your copyright on this.
Yeah, no problem. So I'm Matt Trainer, engineering manager working for RWM, Radioactive Waste Management.
Hi everyone. Do you want me to introduce?
Yeah.
Of course, yeah.
So I'm Celia White, and I'm a technical integrator for the Strategic Waste Programme in Waste Management for RWM2. Over to you, Matt.
Thanks, Jabba. Could you go to the next slide, please?
Okay.
So, morning everyone. We're going to talk briefly today about the positives and negatives of thorium as a fuel source. Next slide, please. So just a little intro about thorium itself. Basic element of metal, naturally occurs as Th232. It's more abundant in nature than uranium, roughly 3 times. It's fertile rather than fissile, which we'll come on to in a bit. And the fuel can be used to breed fissile uranium-233 to be used in various kinds of reactors. Next slide, please, Jawad. And Celia is going to talk about the positives.
Thank you. So I looked at the advantages of using thorium reactors, and these are sort of summarised on the slide. But the first one around abundant availability. So as Matt said, it's estimated to be 3 times more abundant than uranium, according to the World Nuclear Association. And the deposits are predominantly found in like Brazil, Turkey, Norway, India, and United States, to name a few. The next advantage, was around suitability. So it can be used as a nuclear fuel in several reactor types. So such as molten salt reactors, pressurized water reactors, heavy water reactors. And then the next one was around safeguards. So as a thorium-based power reactor, fuel is a poor source of fissile materials, so it can be used to make explosive device illegally. But so proliferation is said to be sort of vastly resistant compared to the uranium-plutonium cycle, and that occurs uranium-232 can then lead to the formation of a strong gamma radiation field from the decay of uranium-232. So the heat from the gamma.
Can I ask you to go through the safeguards again? You made a very valid point there, but I didn't. There was some noise. We didn't quite catch that. Can you just go through the safeguards again about making bombs?
Yeah.
Sorry.
Yeah, that's fine. I'll start again. So as the reactor fuel, as the thorium-based reactor fuel is a poor source for fissile material, it can then be used. That can be used to make explosive device illegally. So proliferation is said to be vastly resistant compared to the uranium-plutonium cycle. There's that association with forming a strong gamma radiation field. And then, so the heat from the gammas then makes weapon fabrication difficult. But I also saw that, I don't know whether it's correct, but a hypothetical proliferation concern around using thorium is that proactinium can be chemically separated after it's produced. And then that will then decay directly into uranium-233. So, but then I think the advantage of that is that proactinium has a half-life of 27 days. So I think once the waste is safe, weapons are then sort of out of the question. So, and then another advantage is around nuclear waste production. So there's obviously less nuclear waste production with this. So there'll be need to have fewer storage facilities required. And then disposal capacity would be smaller. And then finally, around safety, compared to uranium mining, it's thought that thorium mining would be safer and more efficient, as I think they use open pit for this type of mining, and the thorium ore is, I think it's pronounced monazite, it generally comprises of significant amounts of thorium, so it makes extraction more cost effective with fewer effects on the environment. So yeah, that's all my positives, and I'll pass back over to Matt.
They were very good, actually. Well done, Celia. I liked it, especially the safeguards.
Thank you.
Thanks, Celia. Can we move to the next slide, please, Javad?
No worries. Oh, sorry, I've gone too far.
So I'm going to talk about the negatives of using thorium. So yeah, the kind of points I'm going to run through on the screen there. To start with, there's very high startup costs. There's huge investments required for thorium reactors, as it requires a significant amount of testing, analysis, and licensing work, as it's not been used as much throughout history as the uranium cycle power reactors. There's a huge amount of uncertainty with building these new reactors. So potentially for investors and the commercial side of things, it's not potentially going to immediately make money and be commercially viable yet. And going on nicely to the second point, there's a relative lack of experience compared to the more conventional uranium plutonium fuel cycle. Again, this adds a large amount of uncertainty, and especially getting licensing and investment. Thirdly, whilst it's an abundant fuel source in many parts of the world where they don't have uranium, it still requires a fissile material to start the process. Mm-hmm. So you still need to gain access to some sort of fissile material, which, as we heard on Monday, is what India have spent the last few decades trying to do, is get access to that initial Kickstarter. So that's an issue if you don't have access to that. As we spoke about before, there's a bit of a proliferation benefit, that it would be difficult to steal the material because of the gamma rays. That's also quite a big negative in terms of safety. It produces quite a lot of U232, which can decay and release gamma rays, which is very hard to shield, so it requires a more expensive spent fuel handling and reprocessing. Likewise, the fuel is a bit harder to prepare. Thorium dioxide melts at 550 degrees higher than uranium dioxide, so the equivalence of Westinghouse to create this thorium fuel would have to have a lot more higher temperature and energy to produce that fuel. And then, as a bit of a counterpoint to the proliferation, while it is safer than the uranium-plutonium cycle, you will always have proliferation issues. If you've got to have that fissile material to start it at the beginning, that that fissile material could pose a proliferation issue. And also, as Celia mentioned, there is the ability to create U-233 from the thorium process. And the US and India have successfully tested bombs made from U-233. So the IEA have still categorized certain levels of safeguard on U-233 as a proliferation threat. So it is a lot better, but there are still potential issues there. Next slide, please, Sawad.
Yeah. Before you go on there, I think I like the negatives that you picked up. They're absolutely valid. Especially the lack of experience is something that they've never spent money. And if I am the stakeholder, I want my profit as soon as possible. The high startup is very expensive, and also the gamma rays. This is the most important part of it. Unless you're prepared to spend huge amount of investment in order to shield it, then you're gonna be you won't be any better off in terms of money making on very early days. But it has potential. So thank you very much for that. We move on to conclusions.
So yeah, as we're not going to really answer this question in a 5-minute presentation, I thought I'd conclude with an open question that it does appear on paper to be the ultimate nuclear solution, but then you have to ask yourself why aren't more countries adopting it, including the UK?
You've actually pinched my assignment. So and I in a roundabout way, I was hoping that one of you would come up with that, because that's part of the assignment that I'm about to release today, and that's very nicely done, guys. These two are
as a bonus for that, then, Jawad.
Definitely, I think that you definitely earned yourself a few more marks than the rest of the group. But this was the desired effect, and I'm sorry I didn't end up finishing my own lecture on this, but in a roundabout way it was deliberate. I will put my own lecture back on. It was deliberate to get to see how you guys actually thinking, or what you've read based on what you heard on Monday. However, that was an excellent presentation, and I would like to see if anyone else would like to ask questions, both from yourself and Celia. Perfect. That I like that.
And we've got one more slide just of our references.
Well, that goes without saying. Again, guys, well, this is another point, that if you're doing an assignment, the referencing is very important. I don't care which method of referencing you do. Two things is important, which as is done in here, Matt, very ably, is the referencing from internet must have a date. Otherwise, people change their pages. And if you go into places like Wikipedia, definite no. Because if you look on the Wikipedia, you can go backwards and find the original source of information that Wikipedia nicked. So that's how you should be able to do referencing. Thank you very much. I'll leave it on the last page and ask students to contribute as questions.
Hey, I hate to ask it, but what do you think is the answer to your conclusion question?
It's difficult.
Be careful, we might be giving the game away.
And tell me in great detail so I can make notes.
Yeah. I think just as a relatively fresh pair of eyes to it, the fact that until now no country has used it just is quite telling. I mean, it's not always the case that international governments make the right choices, but it's the fact that it hasn't been successfully used yet through the kind of boom eras of the nuclear industry is potentially quite telling. But I think that's probably perhaps why I'll be approaching it warily.
Yeah, I think maybe part of it might be that originally, obviously, nuclear power was kind of very weapons-based, and governments were putting funding into it to find weapons. And so the fact that it was proliferation-resistant probably didn't help it. probably didn't help its case because it didn't really breed a lot of weapons grade materials.
Can I add something to that as well? The reality behind it as well, you've got to look at it from the political angle as well, especially, as you know, during the Trump era, which, if you were listening to Mel's lectures the other day, and it's added extra that he added on the when he came on Tuesday, he did say that there was a lot of worry about the fact that they hadn't signed treaties with Russia. So Russia is still seen as a major sort of an arms race competitor. And as such, to give this sort of fuel a chance, the world needs to know that there isn't any sort of aggression possibly going to come from other countries. So until then, they're still going to rely on what they've got, but they've got too much of a plutonium stockpile, especially in America. So as I said on Monday with the lecture, is they need to look at that as well, from the possibility of using the plutonium as a mixed fuel in an attempt to get the thorium going. But the Matt's and Celia's both negatives and positives are very, very valid. And it was quite straightforward. We haven't gone to technology, we haven't gone to chemistry side of it. These are facts that they picked up. I hope that helps. So, thank you very much for both. In a normal class condition, I would ask everybody to clap, but we'll assume that we've done it electronically. So I'm going to stop this and hope to see somebody else's stuff that's been uploaded. So I'm going to stop the presentation and restart again. Recording. Thank you too. Excellent. You're going to get to know all my emails now. Patrick and Simon. Simon, I've got two from you now.
Yeah, I don't mind if Simon wants to go first.
It is Simon Witters, isn't it?
Yeah, that's right. Yeah,
I think
I don't mind
the
going
same
next.
thing anyway, but
There are two of them, so I'm going to your first one. I hope you haven't changed it.
Yeah, I just sent it a couple of times. So.
Okay. I can go to the latest one if you want.
No, it's the same presentation. It just didn't seem to be reaching you.
Okay.
Just impatience on my part.
Right. Are you presenting it all on your own, Simon?
Yes, it's just missed.
Just bear with me a second until I put the recording on again. I can keep them on air. Over to you, Simon.
Okay, so having been introduced to thorium as a potential nuclear fuel and its wide range of benefits from yourself, Javed, in this week, and also that was it Matthew and Sarah that have just alluded to, I decided to spend a bit of time looking into how we might make it a reality. So I've titled my presentation the thorium race, and I'll allude a bit to that as I go through. So go to the next slide, please.
Can you see?
Yeah, that's loaded now. So if you want to get anything nuclear launched out there in the country, then obviously you need to get the public on side, because that's always the barrier, whether it be in regard to costs or where we're going to have these sites, or the renewables argument. So I decided to look into what the main influence were, the papers, and I found this article by The Guardian that warned us not to believe the spin on thorium being a greener nuclear option. So straight away, the first line, they linked it to renewables and the intent the nuclear should be green. It warned that thorium reactors have never been commercially viable, and that they hadn't seen new designs which seemed to be remotely as such. They alluded to the concern that we often hear with nuclear, with the fact that we've already spent billions of pounds on nuclear research, and we've got expensive ongoing reactor construction, and they're also using this age-old argument of decommissioning costs. And again, making reference to renewables, claiming that if we'd have spent the same money on renewables as we do on nuclear, and then they would be in a much more advanced position. So they pointed in the article. They pointed to this ambition to be a net zero, net carbon zero country in a short period of time. So the argument was based on this race between, the development of renewables being able to get to that point quicker than nuclear could. So can I next slide, please?
Yeah. We got it?
Yeah. So that was what the papers were saying. So I decided to look at some reviews by more national focused companies in the hope that they would shed a bit more promotive light upon using thorium. And NNL had carried out a comprehensive review, and their conclusions were that for the foreseeable future, the only realistic prospect of deploying thorium fuels would be in our existing and new build light water reactors, as using a thorium plutonium MOX fuel, and that's being advocated by Thor Energy, and its main benefit being to use or power stockpiles of plutonium. But noted that the utility companies themselves would be unlikely to invest in thorium fuels given that current market conditions. So at the minute, uranium is plenty available and it's at a low price. So, why would they start developing, spending money developing alternative fuels? The NNL also highlighted that India was the furthest ahead with the technology, which is something we've been told this week by yourself and Javad. And I noted that this is despite India not benefiting from the technology shared under the NPT, which is something we've also been told this week. Mm-hmm. So next slide, please. So having looked a bit into what the challenges were from the public's point of view, or I should say the media's point of view, and also the nuclear experienced nuclear organisation, I asked the question, so how do we make thorium fuel? If it is that good, how do we make it a reality? So I looked at the opportunity to align the fuel development, which is what the NNL would recommended was the only viable route forward, with our current PWR projects. So we're building these EPR reactors, and I looked those up and found that they actually completed the generic design assessment process. So it's probably unlikely that we would be changing major aspects of the design of the plant to facilitate thorium fuels. But I didn't rule out potentially developing a thorium MOX fuel. And I also noted the UK is currently early in the phases of looking at small modular reactors. Mm-hmm. So I looked up the UK consortium PWR design, which I noted was based on conventional fuels, so uranium. So there was no plans there to use thorium fuel. Mm-hmm. I found examples of US SMR designs which actually were looking to use up to 20% enriched fuel from military stockpiles. So I sort of started to think, well, instead of using plutonium up by using 20% enriched uranium fuel, is thorium and plutonium MOX a feasible alternative to using up military stockpiles? So So through that sort of review of SMRs, I noted that we've not yet selected a design for the UK, so we're not committed to any particular design. And I also noticed that the US government is collaborating with Canada on SMR technologies, and they set up a collaboration on advanced nuclear technologies with Canada. And they'd also formed a molten salt advisory group, and this was the basis for this is that actually Canada's design for an SMR is a molten salt reactor. And Javad, you'd introduced us this week into the potentials of using thorium fuels in molten salt reactors.
Yeah, I'm glad you picked that up, Simon, on the molten salt advisory group, because I was amazed to see how much information there is on that on the internet. And you can actually become a member to get involved. And the number of very high caliber nuclear scientists that are amongst the advisory group, it makes you wonder. The other good thing you picked up on the thorium plutonium MOX, which I believe we are making through, is it NNL for Norway? I think they've looked into this one through the NNL, but I can't hand on heart get my reference right. But there is something being done on that, so making the mixed fuel. So I would very much like to see in the assignment that somebody put their finger on that, the pulse of what I'm saying in here, because that there's a lot of hidden work going on, not hidden, but unknown, and you only need to go and find out. So I would definitely recommend that when you're doing your assignment to look into that as well. Okay, I'll shut up and let you talk.
Next slide then, please.
Okay.
So from my short review yesterday afternoon, noting the sort of view that whatever we do with nuclear, it needs to be quickly because of this ambition to become a zero net carbon country very quickly, or world. I basically came up with sort of two recommendations really on what the limited amount of research I've been able to do. And my first recommendation, I think, would be for the near term, would be to develop a thorium plutonium MOX fuel for use in the new UK PWRs, because this will give us the opportunity to further develop thorium fuel technology. We can start to reduce this UK plutonium stockpile, which from that would really shine some positive light on the technology and the investment. And it will also give the country some mitigation against future increases in uranium price through reduced availability. And then in the longer term, we're looking at SMR designs for the country. So we should certainly consider that selecting a molten salt design could give us this opportunity for a thorium molten salt reactor in the UK.
I think in terms of safety, as molten salt reactors do offer a better protection in light of the reactor-related accidents as a result of nuclear fuel cycle that we've met this week on the 3 separate uranium-related reactors. So that the thorium molten salt reactor, in terms of safety, where you just unplug in a very, very conventional way and just get rid of the fuel into a different section to stop from, because it's already in a molten state anyway. So, that's one of the biggest worry you've got on a uranium type of reactor is if there's a meltdown, then you are into trouble. As the second today's lecture on the reactor accident showed on both of the Fukushima and the Chernobyl. So this could be another winning point from my personal point of view. So don't quote me coming from research point of view. Okay, right? Any more?
No, just the opportunity to engage with India. And clearly they've done a lot of development on this. So if it truly is going to be a global approach to solving some of these nuclear problems, then may save a lot of money and time in the long run if we sort of pick up where India currently are. There's some barriers to that with the non-proliferation treaty, and they're not currently signed up to.
Yeah. You made
that's all from me. Thank you.
I would want to see on your assignments if any collaborative work is being conducted with India. One of the biggest problems India has, they don't have the money, and hence why they are slow. They're doing it at a very slow pace, but they're well ahead of the world on that. So that's something that I'd like to see in your assignments if you're doing this particular assignment. Do you want me to move on, or?
No, that's all from me then. It's just my reference page.
Don't forget to put referencing, which you have done, guys, if you're doing it. Thank you very much. I'm going to stop this recording and see what the next one is. Next one I see is Patrick.
Yeah, we're happy to do it.
Yeah.
I've received no more. Is nobody else is going to present?
I'll be sending mine in a couple of minutes.
Right, that's okay. Anyone else, please?
Come on.
Sorry, I'm waiting for the recording to come on. Okay. Patrick, over to you.
Right. Yeah, sorry if we're kind of repeating ourselves a little bit. We've even used the same thorium symbol.
It doesn't matter. That's absolutely fine.
Yeah, just go on to the next slide, please.
Okay. Will you introduce yourself and tell us which company you're coming from, because these are going to be archived?
Yeah. So I'm Patrick. I'm just a student at NTEC, just looking for jobs. The same as I think Sam was saying yesterday. So yeah, just on through NTEC at the moment.
That's a good advert for yourself. If you know about thorium, you've got a job.
I'm doing it with Chris as well. So if you want to...
Hi, Chris. Will you introduce yourself, please?
Hi, I'm Chris Christian. I'm same as Patrick, just a student at NTEC looking for jobs as well. Not enrolled at any company yet.
Yeah, so just going through the advantages, this should be hammered home by now. It's roughly about 3 to 4 times more naturally abundant than uranium. Uranium-233, which is formed from beta decay of protactinium, has a high energy density than U-235. For example, 1 ton of thorium in the LFTR would generate the same amount of energy as 250 tons of uranium, which is pretty crazy, really. 98 to 99% of thorium fuel would fission at either 233 or 235. So basically, the chance of neutron capture up to the heavy nuclides are very slim. That's what it's saying. So overall, there'll be less deadly heavy actinides, which pose a lot of problems in the future in terms of storage. So there it says less long-lived transuranic waste. I didn't add the point, but I think as the others were saying, it can be used in thermal breeder reactors as well. As the max fuel. So, you know, if you look at alternate fuels like plutonium, for example, that can only be used in fast reactors because I think I remember the absorption at thermal energy is produced less than 2 neutrons, so it can't actually sustain the reaction required. There's been a bit of a typo there, sorry, but yeah, in the fast high temperatures which have been proposed to be used thorium at, it will actually burn up a lot of the fission products. So again, the waste issue is reduced when using thorium. And thorium oxide has some good physical properties as well. Next slide, please. Yeah, so better resistance to proliferation, question mark. So it's actually the characteristic that led to renewed interest. I think the initial interest was basically to supplement what was thought at the time to be depleting or unsustainable uranium reserves. So this proliferation characteristic that thorium had kind of boosted interest in it. So one of the advantages, as Matt and Celia said, it's fertile, but it's not fissile, which is important. So in itself, it needs to be used in conjunction with another radionuclide like plutonium. It's a hard gamma emitter, making it hard to handle. So obviously that's a benefit in terms of proliferation. In regards to storage, obviously it does make it a little bit harder, but after, it's got a half-life of 69 years, so the activity will be reduced pretty quickly if you look at it in terms of long storage. It can't be chemically separated from uranium-233. So if you use it in a reactor that breeds uranium-233, the uranium-233 that is produced cannot be chemically separated. So you would have to isolate the protactinium in order to just get the uranium-233, which obviously brings a lot of processing complexities there. As I said, it can be used in conjunction, so it can be used to deplete plutonium stockpiles, which is obviously a good thing. Next slide, please. Chris.
So I'll continue from here. So as Patrick was saying, although it may offer better proliferation resistance, it is still not resistant. Thorium can create small volumes of uranium-233 when chemically separated from protactinium-233 during this decay process. And this uranium-233 is the main component in nuclear weapons. This chemical separation can be done in a standard lab with standard equipment. So it can be done away from the eyes of organisations such as the IAEA without arousing suspicion. From previous experiments testing the separation of protactinium away from uranium-233, only 1.6 tons of thorium metal would be needed to produce 8 kilograms of uranium-233, and the IAEA classes this as the minimum amount to make a nuclear weapon. So this production of uranium would take less than a year to make this 8 kilograms, not accounting for potential streamlining and acceleration of this process in the near future. So therefore, this presents a big concern considering the amount of thorium accessible globally. Examples: uranium-233 explosion testing. Sorry, what was that?
It's fine. Nobody said it.
Okay, sorry. Never mind. Examples of uranium-233 explosion testing are Operation Teapot, which can be seen in the picture on the slide, in the US in 1955, where a plutonium and a mixture of plutonium and uranium-233 device was detonated. And in 1998, where India made a small device from uranium-233 called Shakti. Both of these actually produce a smaller explosive yield than expected, but this wouldn't stop improvements to the explosives in the future. A different issue this process presents is that from each gram of protactinium decaying via beta decay, 50 watts of heat is produced. Now, this doesn't seem a lot for 1 gram, but it will be a huge amount of heat when scaled up to the actual masses used, which increases the difficulty of handling and might limit the scaling up of its use in the future. Next slide, please.
Sorry.
So further issues include the production of uranium-232, as Patrick has mentioned before. When thorium is bombarded with neutrons, so that fissile uranium-233 is produced, one of the byproducts produced is uranium-232. This is extremely radiotoxic, and it has a half-life of 68.9 years, and its decay products emit very strong, highly penetrating gamma rays. Thallium-208 is the most problematic of these decay products, emitting gamma rays of 2.6 MeV, with bismuth-212 also causing some problems. And this makes handling very difficult, so much so that a person standing 0.5 meters away from 5 kilograms of uranium-233, containing 500 parts per million or 232, a year after being separated from its products, would receive a dose exceeding the annual dose limit for radiation workers in less than an hour. So therefore, remote techniques and heavy shielding is needed for any of these processes. And this may deter proliferation uses, as it would interfere with weapon makers, the electronics.
That is one of the major points that you need to make sure that this is one of the positive things in a way, that in the wrong hand with the wrong equipment, I don't think they're going to live long enough to be able to do anything with it. So that part of it is quite a good deterrency, if you know what I mean.
Yeah. So it defers the uses because it may interfere with the weapon makers, the electronics, and also makes it very easy to detect, because you can detect high gamma rays quite easily.
Yeah.
Coming back to uranium-233, it is classed in the same safeguarding category, but by the IAEA as high enriched uranium. But it has a significant quantity in terms of safeguards of 8 kilograms compared to 32 kilograms for high enriched uranium, making it 4 times more powerful. These factors may deter terrorists from getting hold of uranium-233 to make weapons, coupled with the fact that you need a research or power reactor to irradiate thorium. But this means the largest security threat is actually from potential proliferator states rather than terrorists. Yeah. Therefore, thorium-related use and technologies need strict monitoring, and irradiating thorium for short periods at a time to create batches of uranium-233 is a covert way to not arouse suspicion from organisations such as the IAEA, which causes potential safety risks. Thank you. Next slide, please.
That's excellent. Thank you.
So Patrick will talk about his opinions first here.
Yeah. On the face of it, we've seen thorium obviously has its benefits in terms of energy density, natural abundance, which will make it more sustainable option than uranium, and it's got a shorter storage character. However, I mean, we've just seen this week, because of the complex nature of the fuel cycle, if you look at it if you're looking to use it commercially, I mean, each step, for example, enrichment and reprocessing are uniquely tailored to processing uranium, which obviously brings its difficulties. The conservative nature of the nuclear industry as well will mean thorium is definitely a distant prospect in terms of using it commercially as well. I mean, I think it's probably gonna take at least 50 years if we were to use it. I mean, that's just off the top of my head. I don't know that, but and again, I think Matt was saying the lack of experience with the liquid fluoride thorium reactor has run for 5 years at Oak Ridge in the US, but that only used uranium and plutonium. So using thorium on a commercial scale, using LFTRs, is definitely still a way off due to the lack of experience. I think one of the main things that I thought about, in terms of my opinion, would it really be worth researching this relatively unknown technology when we have a fully functioning uranium-ran nuclear industry, and we could be focusing on the new gen uranium technologies, like Simon was saying, and I probably think the answer is no for now, but it definitely could be an option for the future, especially if uranium reserves are become depleted. But again, in terms of depletion, I don't think that'll be anytime soon. Chris, if you're going
and just to add on to that, I think as long as careful monitoring takes place and the users of thorium are strictly signed to treaties such as the Non-Proliferation Treaty, I think the benefits do outweigh the proliferation risks. But I do agree with Patrick that thorium nuclear power is not the way forward for the near future, because too much infrastructure and too much method development is needed in too short a time. Because it does present a suitable side project for the nuclear industry. But I do think the primary source should be uranium for the moment.
Right. What about the students wanting to put a question to you two?
So I'd just add that you said 50 years off the top of your head, but 50 years was about the time that the NNL said it would take, so you're a pretty good guess there.
Oh, is it?
Yeah, and also, going back to how I titled my own presentation, this race, everyone seems to be focusing on the fact that 50 years is too long, and it's kind of, well, some of that Guardian article that I read was actually from 10 years ago. So if we'd started this 10 years ago, we'd only have 40 years left. So it's kind of that the sooner you start, the sooner you finish sort of concept. Everyone seems to be fascinated with this race to get this done as fast as possible, where maybe that's not the need. Maybe if we're focused on getting this done quickly because we want to use it as the solution to become carbon net zero, actually, if you flip that on its head and said, well, actually, why do we need thorium fuel? And is it to mitigate against running out of uranium reserves? Well, actually, you've got hundreds of years before that happens. So 50 years wouldn't be a problem if you could switch the focus from the race to becoming net zero to actually this is a solution for when the uranium reserves run out.
But you see, at no time so far any of you referred to the byproduct of the uranium reactors, which now the reprocessing that Harry was referring to, and in light of the fact that the soap is likely to stop forever for reprocessing purposes. So if you continue using uranium, then you still have waste material that's going to need handling, environmentally storing, and all the rest of it, where thorium might have some better options. So
I think Patrick did touch
needs
on
to
that.
be explored in your assignment. Sorry, Christian.
So I think Patrick did touch upon that in his slide, but it's because thorium reactors operate at higher temperatures, so most of the waste products are just burnt away. So you don't have to reprocess them. You don't have to put them underground for thousands of years, like for uranium. But plutonium is a byproduct, and that doesn't burn up as much. But that's kind of the only waste product produced.
Yeah. So basically, that there is a certain positivity factor there, which I was hoping that you would pick up or put your comments in when you're doing your assignment in that angle. Okay, right. I'll stop recording this unless you have any questions.
No, we just got some references, but yeah, thank you.
No, let's have the references on. Thank you very much for excellent work. I mean, to be honest, this is the sort of things I like. By the way, I want your permission to share this with everyone, but I will only share these slides, by the way, after you've submitted your assignment. This is purely because it's to be fair to the people who actually went out of their way and produced this, and for the others to cut and paste and say, report, that's not good enough. So I will release them eventually for the benefit of all of you after you've submitted your assignment. That's if you do the thorium assignment. I think that's only fair, I would say, wouldn't you?
Yeah.
I'm happy with that.
Yeah. So, I'm just checking my email to see if there's any more coming in. We've got Sam.
If you click on the second one, because the first one that I sent you, I just realised didn't actually have a title page on it, so I've just sent another one with one.
Don't worry, Sam. Is there anyone else that is sending?
Oh, sorry. What was that?
Are there any other students going to send any presentation material? I had hoped to have more than this.
Not that I'm aware of.
I've sent you something, Jawad.
You have sent me?
Yes, I think about 5-10 minutes ago.
Under the name of Arshad?
Yep, from my student email.
I haven't.
Is it possible to upload these presentation from my machine? Because I've got few.
If you want to share it, by all means, you can share it directly.
No, I prefer to do it here because of.
Yeah, just bear with me a second. Let's listen to Sam's first because he sent it before you, and then what I'll do, you share your screen with us. Absolutely no problem with that. Let me just get Sam sorted first. Okay, I need to record this, just bear with me a second. Over to you, Sam.
Okay. Yeah, so obviously.
Tell us about your work.
What'd you say, sorry?
Introduce your work and where you're working from and which company you're representing or.
Oh, right, okay. I, much like the people before me, I'm just an NTEC student. I did a degree in mechanical engineering before this and then came on to NTEC. And this, I mean, to be honest, it's probably going to have less information in it than some of the ones that have come previously, and everything you've heard already. But hopefully you'll enjoy it anyway.
Don't worry, just be yourself.
Okay. So obviously, as we've already heard, we're talking about the thorium fuel cycle. If you could get onto the first slide, please. Yeah, so thorium has quite a large abundancy compared to natural uranium, up to kind of 3 or 4 times, which means that it can be a kind of more long-term fuel source if we'd need it to be. It's got a certain amount of inbuilt proliferation resistance, which I'll talk about in one of the next slides. It's got a kind of self-sustaining nature, which just means that it doesn't require any new fissile material once you've reached an equilibrium phase with it, which again we'll talk about in another slide. And it's possible in quite a wide variety of reactors, which is nice, because we don't really have to kind of invent whole new types of reactors. We can kind of integrate this fuel cycle into ones that we've already come up with. So if we just move on to the next slide, please. Second. Yeah, so one of the negatives, but I suppose this is either a negative or a positive depending on how you look at it, is the lack of weapons grade material production. That's probably a negative for the nuclear weapons states that are already present, just because they probably want weapons grade materials. But in terms of general world deproliferation, that's probably quite positive, really. There is a certain lack of R&D that's been put into the cycle so far, just because, as Mel said, the world kind of went down the uranium-plutonium route and never really looked back. Apart from India, there hasn't really been a huge amount of research done into it. So there is a lack of R&D there, which, as people have already said, it'd be kind of 50 years up until working reactors and stuff. But to be honest, 50 years on the time scale of how long we've been around for really isn't anything. and byproducts can have very high gamma emissions. But I'll leave explaining that for, I think, the next slide. So if we could just move on. Okay, so the self-sustaining part of it, all you have to do is provide an initial amount of uranium and thorium. And this means that the thorium breeds, and then the spent fuel is reprocessed, and the uranium-233 is removed. This can then be recombined with the thorium, and then once this process reaches a kind of equilibrium phase, then no more fissile material is required. More thorium is, of course, as the original source, but that just means that you can kind of keep a lack of fissile material moving about, which also provides some sort of kind of safety level, because you haven't got as much fissile material on the move. If you could just move on to the next slide, please. I suppose this one for a lot of people is probably what's going to be the most important thing to do with thorium. Natural thorium itself can't be enriched directly to produce weapons grade materials. So unlike with, fertile uranium and plutonium, you can't just enrich it directly to create fissile material, which you could then use in a nuclear weapon. And also the production of plutonium-239, which is fissile, is really quite low in most thorium cycles that have been proposed already. Uranium-233, which is obviously created in the thorium fuel cycle, could theoretically be used as a fissile material for nuclear weapons. But co-production of uranium-232 within those reactions makes it extremely detectable. For kind of non-state entities to be doing, because it creates thallium-208 in its decay chain, which is massively gamma emitting. So it just makes it extremely detectable. So extremely easy for the kind of global community to deter people from doing it. And I think that is the last slide. I've just got my references after that, but if anyone's got any questions.
Yep. Any questions, anyone?
I really won't be surprised if anyone doesn't, because I feel like all the questions have probably been
asked. Excellent work, actually. Thank you very much. It looks good. And again, you've all followed the procedures on referencing appropriately, which I'm very grateful. I'm going to stop this recording now. And then
Sorry, it's a bit shorter than other people's. Like I said, I was trying to do another coursework at the same time.
Yeah, no, that's good. That's absolutely. At least you've done one better than the one who haven't bothered to do it. So, hint, not getting it. Is Arshad laughing?
Yes, Javad.
Right, I'm going to come off the screen myself and let you. Hang on, it's Michael sent his first. So which one of you is first?
I can. I mean, I announced it first.
Yeah, I'm pulling your legs. Okay.
No,
I'll let you share now. Please share your screen.
Yeah, will do.
When you've finished sharing your screen, and I will record yours as well.
Yeah, just bear with me because I'm not used to using this. So
it's all right. You're the one who volunteered. You only have to send an email to me.
No, I sent that a while back, but then I realized it's not. What do you call it? There's a lot of. I'm using it line by line, so it's not easy to do the way you're currently doing it.
Don't worry about it. That's fine. Is everyone okay? Still up? Still not asleep yet? Are you going to go full screen on that?
I've got a cross, where you upload it.
If double click on your presentation on the left hand side, that's just showing it within your email. The thorium here.
Just bear with me.
No. Would it help if you email it to me, and while I open Mike want to present, so you can email it?
Yeah, that's fine.
Do you want me to do that?
It says if where you upload the thing, it's got a cross on it at the moment. So
it's okay. What I'm saying is just email it to me.
Yeah, I have done.
What did you send on there?
Sorry? Yeah, carry on.
Okay, so I'll move on so we don't waste time. Try to re-email it to me to jyazdani@uclan.ac.uk. Okay. And I'll pick it up. Okay?
Okay.
All right. I'm going to go and present. Okay. Michael, I'm going to put yours on.
Okay.
Bear with me a second, please. Now I need to record this. Over to you, Michael.
Thanks, Trevor.
Introduce yourself, by the way, and your company.
So my name's Mike. I've worked in Rolls-Royce for nearly 8 years now. Obviously, I'm doing the NTEC on the side. So I've quickly put this presentation together. Originally was a high-level kind of assessment of thorium versus uranium, but I found some interesting bits out of it. So changed tact a little bit. Most of it's already been kind of presented, but go on. There's a few things I've spotted along the way. Next slide, please. So in terms of thorium, I started looking. I was going to do like thorium and uranium side by side, but it was just getting too messy. So one thing I found interesting is thorium is actually it's quite easy to mine. Mostly found in I think is monzonite, which is found on beach sands. So you're basically on to open pit mining. Quite cheap, quite easy to do, not too bad for the environment in terms of some alternatives. The overburden of radioactive waste during the mining process is about 100 times less than the equivalent in uranium mining. And the natural thorium is actually almost 100% less topically thorium-232, which is what we want. So you haven't got any enrichment, and it really needs to be done either. But the negative about it, which kind of goes around as a circular argument a little bit, at current, there's no real demand for it, so it's only mined as a byproduct of rare elements. And it's quite immature technology-wise in terms of making it a bit more efficient. However, thorium's got some better uses for if you want to use it as a fuel. The neutron economy, so the amount of neutrons that are produced versus neutrons that are absorbed, really. For uranium-233,
which is produced from the reaction of 232 thorium. And the neutron economy is a lot higher than uranium. So uranium-235 is. Actually, it's actually a thermally safer fuel on its own. I kind of say on its own with a caveat. So it's got a higher melting point and a lower coefficient of thermal expansion, which means if you've got pure thorium in a pellet, you've got a lot less risk of breaching cladding. If you started to get towards some higher reactor temperatures than if it was uranium or plutonium. However, like I said, there's a bit of a caveat there. At the moment, you have to combine that with other fissile materials, uranium or plutonium, to achieve criticality. You're a long way off getting a pure thorium kind of fuel which works, because you need to extract the uranium-233 and put it back in, which has its own problems. So in terms of byproducts and waste, in comparison with uranium, you've got fewer long life transuranic elements, which is good. It's actually more stable. So if you want to use dry storage, you can accept higher temperatures or less cooling, depends which way you want to look at it. It's less restrictive in that sense. However, it's a negative of that in that you've got large gamma-emitting byproducts, which I'll go on to explain a little bit in more detail. And this is when my presentation started to change tact a little bit once I kind of got all this information together. So if we go on to the next slide, please, Gerard. So the kind of viability of thorium really depends upon the fuel cycles that you use. Each has its own advantages and disadvantages. So with an open fuel cycle, the U-233, which is produced and has high proliferation risks, because as other people have mentioned, it can be used in weapons, you burn that up, and therefore you've got less of proliferation concern. You also burn some of the 232, which is also produced on the side, but U-232 has high radioactivity and is an issue for waste disposal. Not saying that's better or worse than uranium as such. We're a bit more mature in terms of waste disposal of radiation, but uranium-232 is quite active. It's quite hard to handle. In terms of the closed fuel cycle, kind of as already hinted, uranium-232 is your kind of Achilles heel. We're going to need a lot of shielding because you're not burning it up. You're going to need a lot of shielding, and it really restricts your techniques to fabricate or reprocess the fuel because of the dose. So you have to get into a lot of manual techniques that either already exist or need to be developed. Uranium-232 can't be chemically separated from uranium-233, which is what you need for fuel, and to re-inject it back into your fuel cycle to get a pure thorium fuel cycle. And it's also difficult to dissolute thorium from uranium anyway. So even if you wanted to get the thorium out and leave the uranium behind, it's also difficult to achieve. So the current stance is, without further development, the open cycle is preferred for thorium because you're burning up the uranium-233, which can be used for weapons, and you have a slightly bit of simpler waste management system. Disposing of the waste arguably has less human contact than if you are having to reprocess it. However, it's still there. It's still got to go somewhere. It's still going to affect people or the environment in some way. So it could be argued there. Next slide, please. The thorium itself, there's a lot of circular arguments with it. Kind of really struggled with it when I was reading through it last night. And there's a lot of things which hold it back. So in the balance of arguments, uranium is seen as highly abundant. We know it. The technology is very mature because of all the investment that was put in from its military applications back in the day. And we can reprocess it. But thorium, it's quite immature on an industrial scale. It's bound with increased radiological risks. As I was getting to in the last slide, getting the closed fuel cycle is your challenge. It's very reliant on existing fuels until you can produce a pure thorium fuel cycle, as I mentioned. But that's, again, going back to closed cycles, which is a high radiological risk, which we don't really want, and it's hard to justify. However, if you go to an open thorium fuel cycle, it doesn't fit with the political, social-economical image of green energy. That's the topic of the day. That's what everyone wants. But if you're going to say what you're going to do with this fuel, well, we're going to chuck it in the ground and we're not going to extract anything from it after we've used it, it doesn't really sell very well. And where I kind of got to this was, it's immature. We need a lot of investment and a lot of development to kind of make the thorium a bit more economically viable. But there's no economical benefit at the moment because uranium does the job. And thorium just brings a lot of issues with it when, again, thorium does the job. So why would you want someone, if you go speak to a bank or a government, until uranium runs out, you just can't sell it. Again, we don't mine thorium specifically. It's a byproduct of other rare elements. We don't go looking for it because you can't use it in anything else either. So the business case becomes very difficult to achieve. And I don't think it's really worth pursuing.
Is that your personal opinion?
Yeah. I think there's a large amount of risk, technical risk involved. And
can I ask a question then? If there's a large amount of technical risk, if we fear about trying something just in case of there are risks, we'll never get anywhere.
No.
So I agree with some of your arguments, but obviously the personal opinion sometimes is very, very individually tailored. But I would argue that aren't we putting too much reliance on the technologies available with uranium and also the issues that, yes, during the use of it, the energy that we take from it, but the background work that goes on the waste management side of it is far too taxing than probably this will offer. And why shouldn't we try new technologies? Because we've learned from uranium experience. So some of the learning curves is already there. So we won't have to make the same mistakes that they did when they were designing their facilities. So therefore, there are merits in both. But as an engineer, you're an engineer. As an engineer, one of the most primary things that we have to have is forward thinking and fail-safe mechanisms. And the fail-safe mechanisms that we have got to learn if this uranium suddenly finishes or whatever, at least we've got some alternative. That's why we went to the renewable energy engineering. We all know that after 20 years of trying I was saying yesterday, the technology there, or the photovoltaics, it took about 11 million square meter will provide one a nuclear power station power. So therefore, we've got to learn. So if you're investing on those 11 million square meters of solar panels, needs cleaning every day. Every time it rains, it's going to stop their energy depreciating in terms of efficiency. So yes, I agree in certain point.
Why are you so anti-solar, Jawad?
Sorry?
why are you so anti-solar, Jawab? You could use the same argument for saying that.
I'm not asking, that's a personal view. I'm not saying that. What I'm saying is, we seem to be saying it's too much to learn. Let's just put it on the side. Is that what we are all saying?
No.
No, I think just because it's got a lot of technical risk doesn't mean you shouldn't develop it. But when you're trying to encourage people to invest large amounts of money to develop this technology, when you've got a viable product already on the table, it really makes it hard to justify. When, if we didn't have uranium or uranium stocks were starting to get low and we had no other opportunity, then this is definitely a way to go. But sadly, until that time, you're asking people to spend, well, companies, not really people, but you're asking for major investments, millions upon millions of pounds to develop something which we've already kind of got a product for. It's got its own unique risk on itself. So it's a circular argument. It seems great theoretically, but in the real world, until that day comes where you need an application, uranium's run out, or renewables aren't going to keep charging our electric cars, and our national grid utilization's sky high now, and the lights are starting to switch off. Until you get to that point, I think it's hard to justify. Like if you go back to the 40s and 50s, the reason why people looked into uranium wasn't for a power source; it was for a weapon. That was the driver. Here, and we've got uranium now, and the lights are on, and everyone's happy about it. And well, not happy about it, but everyone's comfortable. But until the need is there, I think thorium isn't really worth pursuing.
Yeah,
but
that's fine. That's absolutely fine. Any other opinion on this, guy? Is this your last time?
What I was thinking, if you rush into it too much, like maybe in like 10, well, you never know, maybe in 10, 15 years, a better technology comes out with like dual purpose, because thorium's quite single purpose at the moment. So maybe in like 10, 15 years, a new technology comes out where, like it has a lot more positive purposes. So it might be better not to rush into thorium straight away before we use we use uranium a bit more. And then do a bit more development, and then a better technology may come out.
And you've got a very positive point there, actually, if you think in the long term. Thorium is going nowhere. It's going to be wherever it is for thousands of years if you don't touch it. So therefore, why not leaving the use of that for the future generations of a great-grandchildren to use it? I agree with that entirely.
Because thorium is not going to run out. Like, it's not going anywhere.
It's not going to go anywhere. It's just sat there waiting for somebody to use. Similarly, the oil that was under the ground for many, many thousands of years until we decided to dig it out and burn it, and then find out that it's actually destroying the environment. So, let's get rid of the carbon-free scenario. I can agree with both of the arguments. But then at the same time, we can see what India is doing, because obviously, for them, it's a source of income. So therefore, he who gets there in the technology side of it is going to have the upper hand. And obviously, they've invested quite a bit of money on there. So we could learn from their experiences. So the argument it swings both ways, really. And it's really, at the end of the day, the matter of opinion. But for the course for this week to run, we have to have some alternative to argue about and compare, otherwise you learn nothing. You just come and do uranium fuel cycle every year and go away. So it would be nice to have a bit of a view on alternatives, and hence why we've got this bit of a presentation here. So everyone's opinion has a right positive approach into it. So no one person is perfect in saying trying to sort of push their own opinion on the others. It's not that. You're just trying to delve into your opinion to see if you can find the common ground to go forward with it. Okay, right. Have you got any more to do on this one? Or is there any more?
No, that's it. Just a reference.
We have references, obviously. Yes. Okay, so if you're happy with this, I'll stop recording unless people have questions to ask you.
So I've got an observation just from something Mike touched on in some of the earlier presentations as well, and it's in regard to the open versus the closed loop fuel cycle. So in the open cycle, you've got this need for plutonium to start the process. So that was the positive, that we can start to use up the plutonium stockpile. But then if you're using plutonium and you're not making use of the 233, all of the 233 that you're producing, you're then replacing plutonium, which is an alpha emitter, and from a radiation point, much easier to store and deal with than the 233 that you're replacing it with, which is a high gamma emitter. So the proliferation of plutonium is more difficult to manage. But actually, as a radioactive emitter, the 233 is the harder one. So you're effectively replacing one cost with another. And then, so if you present the closed loop cycle as a bit of a argument as to, well, we could actually use that gamma emitting 233 as the Kickstarter and get into this closed loop cycle, suddenly you're not using up your plutonium anymore. So it's almost, is the benefit, it's almost, there's so many circular arguments where now we're either going to replace the plutonium with 233, which is harder to handle, or we're actually only going to use a very small amount of plutonium because eventually we'll be running on the 233 in a closed loop cycle.
Mm-hmm. Any comments on that, those who presented?
No, I agree. To be honest, the circular arguments of thorium is where I really struggled with kind of researching this. But yeah, I take the point.
That's the intended outcome, which I'm quite pleased that you're picking up. So yeah, but we'll leave it at that for now, and we'll move on to the last presentation with Arshad. And unless there's about the question, guys, where is the? No one has actually come forward with the accidents. Yesterday, one of you guys mentioned that
I'll cover it, Jawad.
You are? Is that what you're doing? Sorry, I shut up then.
I knew everybody would be looking at the technical details of thorium, so I thought I'd take the other.
Good on you. That's brilliant. Thank you.
I'm still covering thorium, but it's rather indirect way.
Yeah, no worries.
The reason why I didn't do accidents because I've just finished a massive coursework on Chernobyl, so
yeah,
that's kind of the reason.
Yeah, that's absolutely fine. The student told me that last year, because we had changed from exam to the assignments, so on N01, I believe, they were asked to do the accidents as their final year assignment instead of the exam. So I think people are absolutely saturated on that. So
even this year for anyone, we had the exam and the assignment as well. We had to do both.
Yeah. So I will try to record this, Arshad. So
yeah.
I'm just waiting for the recording to kick in. Okay, just hang on. I should first introduce yourself and then tell us about your work.
Yeah, my name is Arshad Mohammed. I'm a returning mature student. I have a physics background, but I've had several careers already as a software engineer, as a head teacher. So I'm just returning to education. And particle physics and nuclear physics was my interest as a student in the first place. So it was naturally the right place to come to. So that's why I've joined the NTEC, because I have a lot of friends in the industry as well. So. Right. I think the more I've thought about, initially I was very enthusiastic about thorium for all the reasons people have already covered about its competitive energy output and its safer issues and non-proliferation, etc. But the more I thought about it, the more I like uranium. And a lot of the points have already been covered. But my approach to this is slightly different. I'm going to be arguing for uranium in the sense that uranium, in terms of nuclear energy alternative to all the other carbon emitters, is probably the only solution. And I'll try and argue that case. If we could just move on to the next slide. Now, this is where the difficulty is going to be, because I originally did this so I can click it on line by line. But if you could just click about 2-3 times and just stop there, please. I think somebody mentioned, I covered the nuclear accidents for the one previous, I think it was N01. And I thought during while I was doing that assignment that uranium was very hard done by it. I think all these accidents, the 4 or 5 main ones that I've listed above, were totally avoidable in the sense that a lot of them were due to poor reactor design or facility design. If I, for example, take Fukushima, it was known. I think even before they designed the reactors, etc., and they were doing analysis prior to this, they knew that those areas were prone to earthquakes and tsunamis, and there was evidence elsewhere in the world about the size of the tsunamis, etc. Yet, when they put it together, they made 2 critical mistakes. One was that their barriers was 6 meters tall, which was totally inadequate. And I think about 10 years prior to the accident, some of the analysis the local agencies did showed that they could expect 15-meter tsunami waves, and they sat on it, and I think they were going to review the findings, etc. And to make matters worse, they actually put the emergency supplies or emergency power sources underground. So that was just a disaster waiting to happen. If you look at, for example, Chernobyl, that was again. So somebody mentioned during the course of this module that you wouldn't be allowed to put a RBMK reactor anywhere in Europe because of its inherent design faults. If you look at Windscale, I mean, Windscale was. You could argue that that was the beginning, and it was a national interest, and we were fighting for survival at the time, etc. But that was an extreme, another accident waiting to happen. To make matters worse, because of the race we were in, they kept cutting away the safety margins. If you look at the fuel radiators, they kept raising temperature, etc. And it was inevitable that there was going to be a fire. And they designed very nicely with the coolant by oxygen was not in hindsight a smart move, but at the time I think that was the state of the art. So and they did the air cooling because of the perceived danger of water cooling. They felt that was a riskier option. So a lot of those accidents had something to do with reactor design or facility design. On top of that, if you add poor regulation, Windscale, I mean, no regulation at all. We were right at the beginning, at the cutting edge. If you look at, for example, Tokemura, they were inspected so many times, and they had regular monthly, I think, visits. but nobody picked up on all these efficiency changes those operators were making. Their colleagues in the organization saw them doing all these things. They knew better, but they didn't, they didn't support them in that. If you look at, for example, Chernobyl, similar sort of thing. The next bit is that the poor training. I don't think the guys at Fukushima had any inkling of the sort of challenges they would come across in any training they received. Tokimura guys didn't even understand the concept of criticality. They believed that as long as they kept the solutions in liquid form, they would not have a criticality. So, and TMI, I mean, we had operators who had expertise in the naval nuclear reactors, and I think perhaps if they had a fresher, more thorough training in modern civil reactors, or particularly the step change in terms of size, perhaps they would have fared a little better. If you click just one more time. Yeah, and the other bit is I think TMI probably wouldn't have happened if they'd actually carried out a more regular maintenance, particularly on that poor valve. They left it to the next nuclear fuel cycle to, the fuel replenishment to actually carry out all these repairs. I think that was totally avoidable. So all in all, I think all these accidents, I know people talk about, I remember reading about William Penning putting it down to error of judgment, as he diplomatically put it. But I don't think these operators had any chance of making any other judgment. You can only make good judgments on good information. And in those situations, they did not have good information. TMI, for example, they talk about critical alarm systems being placed all over the place so that they were not readily accessible. You've got poor information coming through. I think they had a very low-speed printer that printed out. Not that they would have had time to read the printouts. So all in all, I think all of these accidents, in hindsight, had they followed the current norms, probably would never have happened. I think we are right now in a very good place in terms of regulation, in terms of the varieties of tried and tested designs across the world, in terms of the lessons learned, the sort of things. It's all these accidents actually have led to improvements. We would rather not have had them, but learning generally takes place when you make mistakes. I think with the exception of Chernobyl and Fukushima, I think the mistakes have not been costly, costly compared to other similar industries in terms of number of deaths, etc. So I think accidents, perhaps we should have done a lot better, but right now, in terms of safety, we are in a much better place. And I wouldn't say there won't be another accident, but it would be very difficult under the current arrangements to go back to those sort of major accidents, says he. So I think uranium. Sorry?
You're very optimistic. But
I'm very optimistic in the sense that,
apart from wind scale, which in terms of date goes back a long time ago,
yes,
UK has never had anything as bad as these that you're mentioning in here. And again, in terms of, to be fair with the Japanese, the biggest problem they've had, they follow rules. If you tell them a certain rules have to be done, they follow it to the letter. One thing they didn't tell them, that what if tsunami happens, and how high your protective walls should be. And thirdly, when you put your diesel generators at so many meters below the ground level for your auxiliary generators, So when the water came in, it got mixed up with the generator fuel. So how can then auxiliary generators continue running to provide the cooling water necessary to cool the reactor? So there was a lot of judgmental errors.
I think the more puzzling thing is that in Japan, they had done a lot of, in the interim from the time when they've put up the power facilities to the time when the tsunami happened, they had carried out a lot of studies. And in one of the previous simulations, they'd actually realized that the danger of tsunamis, that they actually raised some of the turbine pumps. Sorry?
Yeah. They did raise, yeah, you're right.
Yeah, they did, but when they subsequently, about 10 years prior to the accident, when they realized that there's a possibility of, tsunamis of similar sort of magnitude as actually happened, they didn't do anything about it other than the fact that they were going to review the research, etc., and just to make sure before they make any changes. You'd think that if you realize that something catastrophic can happen, they would have taken some action.
Of course they would, yeah. It's just, in terms of the management of it, I think they failed. And what you put your finger on the poor maintenance, you see in UK, one of the biggest things, the first thing you learn in engineering, preventive maintenance.
Yes.
Scheduled maintenance and historically planned maintenance. This is why we have nuclear reactors outage. The nuclear power stations outages, which we meticulously go through. If you were listening to Richard yesterday, they go through meticulously planning for every eventuality that they could fit in on that 6 weeks or 8 weeks outage. And obviously, it's a fantastic time to make a lot of overtime. So they do fit in. But if you don't have preventive maintenance, if you don't swap the equipment around, if you don't repair those leaky valves here and there and everywhere, accumulation of that can lead to possible disasters. And again, they didn't do that.
I think the point I'm trying to make in this is that all of these accidents have occurred because of an inherent weakness, despite the fact that a lot of the reports, and I actually looked at some of the lectures, etc., where they talk about poor, operator judgment and errors being made. I don't think, I think those poor operators should be, patted on the back and made heroes, because they made the best judgments they could in the circumstances they were placed by somebody else. And it wasn't because of their incompetence that these things happened. It's just that either they were not trained properly, or they were, they had inherited a system that was, sooner or later going to be involved in a major accident.
Yeah, and but design discrepancies as well, which later on gets blamed on operator error, is not fair either. Like I mentioned this several times on the 3 Mile Island. The designer had done his valve to open when it was under pressure and to close. But if it didn't, so really operator error was getting an error that had no relation to it. It was hours after they realized, oh, hang on a second, that valve hasn't shot even though pressure is released. And that was the major thing.
But the sad thing is that because of their lack of training, TMI, I think when those pressure injectors kicked in, the accident would have just fizzled out. It would never have got to that stage. I think if that TMI is purely, I think, down to proper training of and maintenance that accident happened. Anyway, I think we'll leave it on the. If you could just click a couple of times, and we'll go on to the next point.
I'll just put them all on.
You might as well. I think if I look at the uranium, I think we got about 60, 70 years of development under our belt. We got so many different reactor designs. We got efficiencies, particularly if you look at the CANDU reactors efficiency, heading towards 50% performance. I think, and the developments continue. There's so much background. There's so much. We've gone through all the major accidents. We've learned a lot, and we've got 60, 70 years of learning that we're sitting on, and we've got a variety of different designs to take forward or discard, and it's a bit like being in a sweet shop. You can pick and mix as you like going forward, and technologies are developing. Now you look at fast reactors are coming on, and to me it makes complete sense just to take on the fast reactors with the current fuel cycles. If you look at fuel cycle, every stage of it we have developed. If you look at the mining aspects, we're talking about the new technologies of leaching, in situ leaching, and if you look at every step of that cycle, it's been tried, tested, developed. We've gone, we've improved each and every stage of it. I was impressed yesterday when we were looking at the manufacturing facilities at Springfield yesterday. I think we've got it almost to an art form, and developing it further, I think makes complete sense to me. And on top of that, with the supplies as abundant they are, particularly with the plutonium resources left over from the past.
But you also noticed that they've got no more contracts. Have you noticed that?
Yes.
So do we need to bring this to an end, by the way, because we have also got Mel joined us, with the last session. So if you could make your point on that.
I think what I'll do is I was going to talk about waste, and in the sense that if you look at the developments in waste processing, we are now producing a fraction of the waste we used to produce. So again, changes have come on and helped us manage the waste a lot better. And going forward with these breeding reactions, etc., we like to reduce the waste even further. I suspect eventually we'll get to a stage where the most waste we'll be looking at is the long-lived fission products, which we can store in smaller quantities. Now, there's just one point I think I want to cover, and that's there is a reason why you might want to. Can you click on that supply hyperlink on the side? Right at the top, on the right-hand side at the top, supply.
Okay.
I want to cover the reason why thorium is the way forward for some. If you look at the world supply, this is the uranium supply across the world, and you notice that that major. India is a population 1.3 billion people, and that's a lot of energy that they need, and they've got no uranium. Same with their neighbor Pakistan. And if you look at the swathes of Europe, etc., there's a lot of places where there isn't any supply of uranium, even though it's cheap and abundant at the moment. But just like we went to, we had the Suez crisis over energy security. Everybody wants energy security because it's the national. Not having it makes you vulnerable.
That's what Mel was trying to say the other day as well. The energy security, and Suez Canal played a major role on that. So
that's right, and that's why I think when we're going through Mel's history session, you notice that nuclear became popular every time there was an energy crisis. And that's because everybody worries about being vulnerable and not having energy in this day and age. Nobody can afford, because you go back to the dark ages at the pace where the countries are developing. If you just click onto move on to the next slide, and I'll.
Okay, did I come out of here?
No, just go down. There. This is I think it's a bit of an old what do you call it?
Thorium thing, yeah.
Thorium map. But it actually shows you that, look at that big blob on India. They're sitting on a mountain.
Gold mine.
Yeah.
Gold
so
mine.
For India, it makes complete sense for them to follow the thorium route because it gives them long-term energy security. Look across the world, Brazil and Turkey, for example. For these countries, it's in their long-term interest to invest and master this technology so that they become self-sufficient in energy resources. And that's the reason why I think, other than, they've got longer, Indians are also involved in fusion technologies along with France and US. And I think they're doing exactly the right thing because that once they've got energy security and they've also got plenty of land for food, etc., they put them in a very strong position going forward.
You're absolutely right. But looking at this and looking at the thorium, as I said earlier, this is going nowhere. This is an investment, sat in mountains, whatever. All these countries, this is their futuristic income. Yeah. So therefore, they looking into thorium and possibility of using that, not in an immediate future, but keeping your eye on it and learning from the techniques that are being learned in India and others will play a major role for the future. This is why we've left it to your individual opinion. This is no one person's personal opinion that we must all give up everything we are doing and go walk through getting the thorium reactors off the ground. However, the knowledge of the engineers like yourselves for that, and these students that have got a life ahead of them, 50 years on, they will only just get into their 70s or 80s. It would be nice for them to know that I knew about this and these are the techniques we could probably influence for the future. That's the intention of the course, really. So I shut up and let you finish it off because
I was just going just a last comment. I think it makes complete sense for India, place like India, Turkey, and Britain, for example. We don't have either of these to carry on with these technologies so that we can participate in the future, so to speak. Because it's not just a matter of selling; it's also a matter of having that knowledge to be able to be sitting on the table where these things are discussed and benefit from it. Anyway, I'll end at that. I've taken long enough.
Thank you. Don't forget to put references.
They are but unfortunately I'll put them on the notes to the slides.
Yeah, not to worry. Thank you very much for that. So guys, we can have 5 minutes or so. We'll resume at 15:15. Gives you guys a bit of a break. While I will also, in the meantime, use the opportunity to have a chat with Mel. Is that okay? I'm assuming that's a yes.
Yes.
Thank you. So, okay. I'll stop this recording first before we... Hi, Mel. How are you?
Morning, Javed. Everybody.
All is well?
I'm enjoying a cup of coffee at present.
Good.
I just came in at the back end of that. That was very good.
Yeah, this was what the students do during the week, and this has become quite a habit of mine. There was a very small little reference to thorium in the early years in 2010-11, and the last 5 years I've increased this by asking students to do 2 exercises, because the nature of this course is for students to do some research in situ during the course and then put their opinions. So one is on the nuclear accidents, which they look into, but we provide some reference points like 3 Mile Islands and the Fukushima and the Chernobyl and such like, and we look at the accident related to uranium nuclear fuel cycle related things. And also we look at can thorium be the future non-proliferation entity hat on of the futuristic reactor designs, which we know India is heavily involved with that, and we go through a nice podcast from BBC as well, where it's really, somebody has done a fantastic work. It was done 5-6 years ago, but it seems to be picking up momentum now. So the students on the final day, after all the lectures taking place, they put their own angle to it, and you just missed quite a few very nice presentations by the students from various locations. So, and basically it brings us to the session that we are going to have. I'll be releasing the title for the assignment, as well as feedback on things that they watched over the week. In your absence, we also had a fantastic collaboration with Westinghouse through Springfield, where what we used to get given as a tour, we had the actual presenter and also the head of the Westinghouse, Nick Jones, made sure that this chap would come over and present what happened at the Springfield, which was very nicely done. And that was quite good, because through the week we've gone through the milling and through the various parts of it, the history through you, and with the Westinghouse showing us how the strings are designed for AGR and PWR. And we moved on to yesterday morning, where EDF came from Hisham Power Station, which we had recorded it last week. Incidentally, the lad who recorded it had first signs of the COVID-19, and because he'd recorded it, his colleague came yesterday, and I banned the other guy to come in, even though apparently he'd gone a bit worse from the few days ago. He's still all right, but it's just had the... So we had this fantastic presentation on what happens on the fuel route when the fuel arrives. Arrives at the Hisham Power Station, and going to the fuel journey through the pile cap to the lowering the rods into the reactor, and then ponds, and how it gets loaded back on trucks on their way to Sellafield and such like. So we've had a fantastic journey through real life experience from people that live it. So that was quite interesting. So basically, we are now just going to give an assignment to the students to do over the coming weeks, and also any feedback they want from you as well. Now that you're here, would be useful. They've enjoyed watching your stuff.
I noticed on the last one they made mention of my talk. So.
Sorry, I didn't get that.
I say that I noticed when I came in on the last one, they were making mention of my talk in terms of the...
They did watch it. They enjoyed it, actually. Apart from one or two hiccups that you remember, we had the cameraman came to take some pictures.
Oh, that's right.
We messed up the beginning of the non-proliferation, and the other one was the supply and demand. But nevertheless, they've had over 90% of it quality recording that. So actually, in a possibly for next year, we should really, you and I, just record this on just a one-to-one basis and keep a good quality historically for the future. That would be very useful.
Yeah, I think it'd be a good idea. At least it's a good insurance policy if we ever get into this situation again.
Yes, it is, and also people. It's still fresh in your mind. It's not that long ago you were doing this, and it would be nice to have your angle